can start the class now. So can you hear my voice?
Yes, sir.
Yes, sir. Good. All right. So okay. So I'll start with start class with continuous spectrum. Okay. So far, so what we have, so we have been talking only about operator with discrete eigenvalues, or in other words, discrete spectrum. Okay, so for example, we say that if we have an operator A, uh, then the eigenvalues are A1, A2, A3 up to An. Okay, so this means that the this operator has a discrete eigenvalue. All right. Uh, but in quantum mechanics, however, in quantum mechanics, there are operators with continuous eigenvalue. So, for example, if we take Pz, okay, so this is a Z component of momentum. So this has continuous spectrum. This is continuous spectrum because the momentum of a particle can take any real value from so the value of so the Z component of momentum can take any value from minus infinity to plus infinity. Likewise, the x and the y component can take any value from minus infinity to plus infinity. Okay. So this means that the momentum the momentum operators have continuous eigenvalue. Likewise, the position operator so x hat, y hat, and z hat. So this position operator also have continuous eigenvalue. Okay. So this means that we have to study vector space which are spanned by eigenstates that have continuous eigenvalue. Okay. So we have to study vector space in which the bases are the eigenstates of operator which have continuous eigenvalue. So such vector space will be an infinite dimensional vector space. Okay. So it will be an infinite dimensional vector space in the sense that so every basis set will have infinite number of basis states, and the study of such vector space could be very involved or it could be very subtle. But fortunately, we can directly extend many of the concept in finite dimensional vector space to infinite dimensional vector space. Okay. So for example, so in finite dimensional vector space, we have this delta function. Okay. So so when we go to infinite dimensional vector space, we can just replace this conical delta function by Dirac delta function and so on. Okay, so before I talk about position and momentum, I just want to lay out the groundwork how to deal with the operator with which have continuous eigenvalue. So for this, we consider a Hermitian operator chi hat which have continuous eigenvalue. Yeah, I think someone is not switching off their microphone. All right, so we consider Hermitian operator chi hat which exhibit continuous eigenvalue. And let the eigenvalue of this operator be all the number lying from minus infinity to plus infinity. Okay, so this is minus infinity to plus infinity. So the eigenvalue of this operator chi hat could be any number. Okay, so it could be any number in this on the real line. Oh, I think someone hasn't. So check that you have switched off your microphone. Hey, there's some background noise. Okay, so chi hat exhibit continuous eigenvalue. So the eigenvalue could take any value lying between minus infinity and plus infinity. And we denote by this. Okay, so we use this ket state chi prime to denote the eigenstates of this operator chi hat. Okay, so the eigenvalue of this so the eigenvalue of this state is chi prime. So this means that so if you add this chi hat on this state chi prime, so you'll just get chi prime times is the state again. Or if you so if you're using this notation, so this will be a state. So chi prime prime will be a eigenstate with eigenvalue chi prime prime. Okay. Okay. So I want to talk about the inner product. So how do we take the inner product? So what does the inner product of this of the eigenstates of chi hat look like? So remember that in finite dimensional vector space. So in finite dimensional vector space, the eigenstates of Hermitian operator are orthogonal to each other. For example, if you take two eigenstates, AI and AJ, okay. So this could so these are the eigenstates of some given Hermitian operator. So this will be orthogonal. Okay, so it's in the sense that the inner product is just chronicle delta ij. So how is this? So how does this look like for the eigenstates of Hermitian operator like chi hat, which have continuous eigenvalue? Okay, so in other words, uh, so what will be the inner product of chi prime and chi prime prime? Okay, so chi prime has an eigenvalue chi prime, and this state has an eigenvalue chi prime prime. So what is the inner product of these two such states? Okay, so here we just simply replace this chronicle delta by a Dirac delta function. Okay, so this is given in equation number 3 here. Okay, so the inner product between chi prime and chi prime prime is just a Dirac delta function. It's just Dirac delta function in which the argument is chi prime minus chi prime prime. Okay. Okay, so this is you have to remember this. So if you have an eigenstate, or so if you have an operator with a continuous eigenvalue, so instead of the chronicle delta function, you have the Dirac delta function. If you take the inner product between any two eigenstates. Okay, so the next thing is I want to write the identity operator in terms of the eigenstates. So I want to write the identity operator in terms of the eigenstates of chi hat. Okay. So for n dimensional vector space, so if these are the orthogonal bases, okay, A1, A2 up to n are orthogonal bases, then the identity operator, you can express it in this way. Okay, so identity operator is the summation from I to n, brush state AI times get state AI. So what does this look like? If we have an infinite dimensional vector space, okay, if we have an infinite dimensional vector space in which the eigenstates of chi hat, in which these are the basis states. Okay, so here we are summing from a equal to 1 to n. Okay, so we have a finite number of eigenstates, but here we have infinite number of eigenstates. Okay, so the eigenstates are this one, for all values. Okay, so chi prime could take any value from minus infinity to plus infinity. Okay, so this means that so the thing which we have here, this summation, we have to replace it by a uh, integral. Okay, so this is what we have now. So instead of a summation, we have an integral from minus infinity to plus infinity, and we also have to include this d chi prime. Okay, so this is and then here we have the same thing. So we have the bra chi prime times the get chi prime. Okay, so this will be the identity operator in the infinite dimensional vector space that we have. So this is identity operator in the sense that if you act this state on any state in your vector space, okay. So if phi is any vector in the vector space, then this will just give you the same state again. All right. Okay, so we already defined the inner product as well as the identity operator. Okay, so since the eigenstates of chi hat are the basis of our vector space, so this is the basis of our vector space. So this means that we should be able to express any state in our vector space in terms of this eigenstate. So we should be able to express any state as a linear combinations of these states. Okay. Uh, so in order to see how any given state is expressed in terms of this state, so what we can do is that we can so we can just act. So in order to see how this state is given in terms of this state chi, right? So what we can do is just we can just act the identity operator. Okay. So we can just act the identity operator on this state and then substitute this thing here. Okay, so this is given here. So psi is same as I times chi. Psi is same as I times psi, and then we put in the expression for the identity operator. Okay, so the identity operator is this. So it's minus infinity to infinity. Del chi primes bra state chi prime and get state. I mean the get state chi prime and bra state chi prime acting on the psi. Okay, so then so we can pull this state inside the integral. Okay, so this means that so when you pull this inside the integral, so what we'll have is the inner product between this chi prime and psi. Okay, so this is what we have. Okay, that's okay. There's a typo here. Okay, so this is just a number. Okay, so inner product are just a number, and this is a chi prime. So you can just take so you can take this on the left hand side. So I have I put this thing here. All right. Uh, so this means that the so from this equation we see that this state psi is given in terms of chi prime in this way. Okay. So the state psi is just integral of minus infinity to infinity del chi prime, this inner product, and then this state chi prime. Okay. Uh, so in other words, the state psi is so the state psi is constructed from infinite number of the eigenstates of chi hat. Okay. So so you take an infinite linear combinations of all the eigenstates of chi hat to express any state, any given state psi. Okay. So apart from this, you can also express this. So this is the ket state. You can also write the dual of this. Okay, so the dual of this is just so I can write the so I can express the dual of chi of psi in terms of uh, the dual of chi prime. Anyway, we will not be using this. Okay, so the other thing is that so if we have an inner product like this between psi and phi, so we can express this. So we can express this inner product in terms of the inner product of chi prime and psi, as well as the inner product between uh, chi prime and phi. So the way to do this is to insert the identity operator. Okay. So here, so in this inner product, we just insert the identity operator here. Okay. So it's the same thing. Because I had acting on phi will just give you phi again. So here we then we write the expression for the identity operator. Okay, something like this. Okay, so when we open this, so we can put everything, so we can pull everything inside the integration sign. So if you do this, so what we'll have is this. Okay, so we have inner product from this. So this is given here, and we also have an inner product between this and this here. Okay, so this is what is given here. Okay, so we're left with this. So inside the integral, we have this inner product between. Oh, so let me just. Okay, so inside the integral, we have this inner product and this inner product. Uh, so here, so this thing, you can write it as so you can switch this through. All right, but if you switch, so if you switch this order, you have to put a star. Okay. So this is the conjugate symmetry of inner product. So I'm using so instead of this, I put this chi prime psi star. All right. Okay, so this is the inner product between psi and phi in terms of the inner product between phi psi and phi with the eigenstates of phi hat. So here, so instead of this, I can also do it for the same state. Okay, inner product between phi and phi. So if I want to find the inner product between phi and phi, so what I have to do is that I just have to change this to phi. All right. In other words, so the inner product between phi and phi is this, as we have already seen. So I've already derived this. Okay. So this is, as you can see, this is, so these two numbers are the same except for a star here, all right? So if you have a number z star z, so we used to denote this by mod of z square, all right? Likewise, I can write this quantity as inner product between the mod square of inner product between chi prime and psi. All right. So this means that so we usually want our we usually want our state to be normalized. In other words, we want the inner product between psi and psi to be one. Okay. So this means that this normalization condition is given by this. Okay. In other words, normalization condition is okay. So are there any questions? Okay, so with this, we can talk about position in quantum mechanics. Okay, so having introduced operator with a continuous eigenvalue, we can now talk about position in quantum mechanics. But for simplicity, we'll first consider a particle which is constrained to move along the x-axis. Okay, so we'll consider one dimension first. So we'll consider particle which is constrained to move along the x-axis before we discuss position in 3 dimension. So here we can further constrain the particle to lie between intervals, say x and xp. Okay, so we can also constrain the particle to. So this is the x-axis. Okay, so we can constrain the particle to move between a and b. Okay, but we'll not put this constraint. So we'll just okay. So we'll not make this further constraint, and we'll allow the particle to lie anywhere between minus infinity and plus infinity. Okay, so the particle could lie anywhere between minus infinity and plus infinity on the x-axis. Okay. So position of a particle is unobservable. Okay, so this is something which we can measure. So there must be an operator corresponding to it. So we represent this operator by x hat. Okay. So the particle could be anywhere between minus infinity and infinity. Okay, so the position of the particle are real number. Okay, so this means that x hat should be Hermitian operator. In addition, it also has a continuous eigenvalue. All right, because it could so the position could be anywhere between minus infinity and plus infinity. So it has a continuous eigenvalue. Because position could so the position of the particle could does not take discrete value, so it's taking continuous value. Okay, so x hat is an operator with a continuous eigenvalue. With the eigenvalue all the number, and the eigenvalue of x hat is all the number lying between minus infinity and plus infinity. Okay, so we denote the eigenstates of x hat by this state. Okay, x prime. So this x prime denote the eigenvalue of. Okay, so this so if you're writing it like this means that this state has an eigenvalue x prime. So in other words, if you are acting x hat on this state x prime, so you will get x prime the same state again. Okay, so this means that the eigenstates of x hat for this state is x prime. So here the x prime are just numbers. Okay, so these are just numbers which give us the coordinate of the particle. For example, if you have a state like this, so if you have a state like so x prime is equal to 0.67 centimeter. Okay, so this means that the so if a particle is in this state, so it means that the location of the particle is at 0.67 centimeter. Okay. Okay, so now so what is the inner product? So what are the inner product of these position eigenstates? Okay, so these are called position eigenstates. Position eigenstates because they are eigenstates of position operator. So what are the inner product of these position eigenstates? So let x this state and x prime and x prime prime be position eigenstates. Okay, so position eigenstates such that this one the eigenvalue is x prime and this one the eigenvalue is x prime prime. Okay, so like the thing which already discussed. So the inner product between x prime and x prime prime is we have to take it to the Dirac delta function. Okay, so this is Dirac delta function with argument x prime minus x prime prime. Okay. Okay, so if we have a particle which is constrained to move on the x-axis, so any quantum states of that particle, we should be able to express in terms of the position eigenstates. Okay. So in other words, the position eigenstates form a complete basis sets in the sense that we should be able to express any state of a particle confined to move in the x-axis in terms of these position eigenstates. Okay. Okay, so this also means that we can write the identity operator in this in this vector space as this one. Okay, so we should be able to write the identity operator in this way. Okay, so here we have so inside we have this operator. Okay, so we're summing over this operator from minus infinity to plus infinity. Okay, so this operator, as we have already seen, so this is made up of this cat state and a brush state. All right. So this is an identity operator. So this is identity operator for states of a particle which are constrained to move along the x-axis. So identity in the sense that if you add any so if you add this on any state, so it will just give you the same state. All right. Uh, so so how do we express? So how do we write this? So if we're having a state like this, so how do we express this? So how do we write this state in terms of x prime? Okay. So we should be able to construct this in terms of the position I can say x prime. Okay, so again, the way to do it is to add the identity operator on this state. All right. Okay. So this is so the expansions of a state in terms of the position I can state is obtained by acting the identity operator on the state psi. So this stays same psi is same as this one. I had acting on psi. Okay, and if you substitute the expression for identity operator, okay, so this is what we'll get afterwards. Okay, so inside the integral we have this inner product. So this is just a number. Okay, so this is so inside the integral we have a so we have a number multiplying a cat state. Okay, so we can just take this to the right hand side. So we have so these are just number. Okay, so the x prime and the inner product is just a number. Okay, so this is a number and this is a state. So this is like a superposition of uh, so this integral you can think of it as a superposition of all the so this is a superposition of all the position eigenstates. Okay. Okay. So this is how we could express any given state psi in terms as a superpositions of the position eigenstates. Okay. Then so now so we can now talk about measurement. So we can talk about measurement operation. So for this, consider its psi. All right. So we may try to find the position of this particle by placing detector along the x-axis. Okay, so we're constraining the particle to move along the x-axis. So we can try to find the position of this particle by placing detector along the x-axis. Then what is the probability of finding the particle at x prime? So what is the probability of finding the particle at x prime when we measure its position? Okay, so if the particle is in this state and we measure its position, so what is the probability of finding the particle at this particular point, x prime? Uh, so we might have thought that this is given by x prime psi. Okay, so we might have thought that this is given by this number if we interpolate a result from a finite dimensional case. Okay. So for example, if we're measuring, so if we have an operator A hat, so if we have an operator A hat, which have eigenvalue A1, A2, A3, okay? And so if the eigenstates of with the eigenvalue A1 is A1, let me just write it here. Uh, so if we have so let's take so let's talk about the finite dimensional vector space. If we have an operator A hat with eigenvalue A1, A2, A3, and suppose the eigenstates with eigenvalue A1 is this one, the eigenvalue is this two, okay? So the probability of getting A1, so if the particle is in the state psi, the probability of getting A1 when we measure the value of A, okay, it is given by this. Okay, so this is what we have in the finite dimensional case. So if we use the same logic, so we might have think that the probability of getting x prime when we measure the position of the particle which is in state psi is given by this. Okay, but we cannot use this. Okay, so we cannot interpret this as a probability anymore due to the continuous nature of the eigenvalue. Okay, since the operator x hat has a continuous eigenvalue, so we cannot interpret this as a probability anymore. So we have to interpret this as a probability density. All right. So we have to interpret this as a probability density. Okay. So this is what I mean. So probability density in the sense that this is the so we are talking about one dimension. All right. So this is probability per unit length. All right. So it's not probability, but probability per unit length. So what do I mean by this? So when I say that what this is probability density, what does it mean? Okay, so this means that the probability of so I have a x here. So this is x prime. So let's take a very small interval. Okay. So this is x prime, and here is this one is x minus delta by 2, and this side is x plus delta by 2. So delta is very small. Okay, so this whole interval will be delta. All right. So when we say that this is probability density, so this means that the probability of finding the particle between in this interval. Okay. So the probability of finding the particle in this interval is given by this. Okay, so so the mode square times the interval. Okay, so P is so the mode square times the interval. So this mode square is just P by delta. Okay, so this is why it's called so it's probability by per unit length. Okay, so this is why it's called the density. So instead of this, what we can do is this one. So instead of this, what we can do is that we can take this small interval to be so the length of this small interval to be dx prime. Okay, so we consider this interval of length dx prime, and x prime is at the center. Okay, so you can take it x prime to be at the center, and we also have to assume that the state psi does not change very much within this interval. Right, so this interval is very small. Such that you can assume that the state does not change within this interval. Okay. So the probability of finding the particle within this interval is given by this. Okay, so it is mod square of the inner product between x prime and psi times the interval, the length of the interval, which is dx. Okay, so you have to remember this. So this is very fair. So this is similar to what you already know. Okay. So instead of this, what I think what you have is uh, chi x square dx. Okay, so I'll tell you how it is related to this thing. Okay, so this is finding the So this is the probability of finding the particle within a small interval. So what would you do if you want to find the probability within a finite interval? Okay, so for example, if you want to find the particle, probability of finding the particle between say A and B, where A and B, so where this interval is not small. Okay, so what you can do is that you can divide this interval into small interval. You can divide this into many small interval, and then you find the probability for each of these small interval. Probability of this finding the particle within this interval. eh, Okay, so the probability of finding the particle within small interval, so you can just use this formula. Okay, so we find the probability for each of these small interval, and then the total probability you just have to add all these probability. Okay, so you just you have to add this probability plus this one and so on. Okay, so if you're adding this, then what you will get is just an integral. Okay, so in other words, for a particle in state psi, the probability of finding the particle between A and B. So you just have to integrate this thing from A to B. Okay. So this is from A to B. So what about the probability of finding the particle between minus infinity and plus infinity? So minus infinity and plus infinity. So what is the probability of finding the particle to be somewhere between minus infinity and plus infinity? Okay, so you just put A to be minus infinity and B to be infinity. So this is the probability. So this total probability has to be 1. Okay, so this total probability has to be 1 because you will always find the particle somewhere. So if you measure it, so the particle has to lie somewhere between minus infinity and plus infinity, right? So this is why this thing has to be 1. Okay, so in other words, this has to be 1. Okay, so this means that uh, if you want to interpret this as the probability density, so we have to normalize our state such that this is satisfied. Okay. In fact, so this thing is same as this one. Okay? So this condition is same as saying that this inner product is 1. Okay, so I'll talk more about this when we go to 3 dimension. So since we discussed 1 dimension, then we can go on to 3 dimension. So if you're using Cartesian coordinate, so we'll use. So if you're using Cartesian coordinate, then the position of a particle in 3 dimension is specified by the x, y, and z coordinate of the particle. So you denote the position of the particle by this number. And we denote the tree operator corresponding to this component of position as x hat, y hat, and z hat. Okay? So in quantum mechanics, there should be an operator corresponding to each observable. So we'll denote the tree operator corresponding to the 3 components of the position by x hat, y hat, and z hat. So here we will use this x prime. Okay, so this is a bold-faced. So this is a bold-faced x. Okay. So this bold-faced x means this one. So this is to reduce the notation. Otherwise, the notation could become very long. Okay, so this bold-faced x prime means this x prime, y prime, z prime. So what is this? So what does this state mean? Okay, so this is an eigenstate of x hat, y hat, and z hat. Okay, so this is an eigenstate of x hat, y hat, and z hat, such that the eigenvalue of x prime is this one. I mean, the eigen value of x hat is x prime. The eigenvalue of y hat is y prime, and eigenvalue of z hat is z prime. Okay, so in other words, if you're acting x hat on this state, so you'll just get x prime, okay, times the same state. And if you're acting the y hat on the state, you'll get y hat times the state. And if you're acting z hat on x prime, you'll get z hat the state again. Okay. So here I'm assuming that we could have a simultaneous eigenstates of the operator x hat, y hat, and z hat. Okay, if you remember our discussion about commutators, so we have said that we can only have a simultaneous eigenstates of any operator if they're all commuting with each other. Okay, so here the reason why we can have a simultaneous eigenstates is that all these so these three operators are commuting with each other. Okay, so in other words, x hat, y hat is 0. Okay, or x hat, z hat is 0, or y hat, z hat is also 0. Okay, so this is why we can have a simultaneous eigenstate. So how should we interpret this then? So how should we interpret this state? So if a particle is in this state, so this means that so you can think of this particle as a uh, so if a particle is in this state, so you can think of this particle as a definite position in which the coordinates are uh, x prime, y prime, and z prime, right? So this is the first point, bullet point here is what I've just said. Okay, so now we can talk about inner product. So what is the inner product between uh, this and this state? Okay, so instead of this, let me just write this as x prime, y prime, z prime, uh, and this one is x prime prime, y prime prime, z prime prime. Okay, so this is what is meant by this. Okay, so we have to take this inner product as a product of three Dirac delta functions. So the first one is this one. The first one has an argument x prime minus x prime prime. The second one is Dirac delta function with argument y prime minus y prime prime. That one is a Dirac delta function with argument z prime minus z prime prime. Okay, so to simplify the notation, I'll simply write this as so to simplify the notation, we'll simply denote this in this way. Okay, so uh, so we'll just write this as delta cube both phase x prime minus both phase x prime prime. So the cube here means that it is a product of three Dirac delta function. All right. Okay, so another thing is that if we have a so for a particle in 3 dimension, so the quantum state of a particle so any state, okay, so any state of a particle in 3 dimension, you should be able to write should be able to construct the state of a particle in 3 dimension in terms of the position eigenstates. Uh, so in other words, these position eigenstates they form a complete basis set. All right. So they form a complete basis set for for a state in 3 dimension. Okay. So this means that the identity operator. So the identity operator for states in 3 dimension, you should be able to write it in terms of you should be able to write it in terms of the position eigenstates. Okay, so you should be able to write the identity operator in this way. Okay, so what do we have here? So here we are integrating this So let's look at this. So this is the position eigenstates, or more precisely, the ket state with the uh, eigenvalue x prime, y prime, and z prime. And we also have this bra state with the eigenvalue x prime, y prime, and z prime. Okay, so this is an operator. As we have already seen, an object like this is an operator. Okay, so we're integrating over the value of x prime, y prime, and z prime. Okay, so x prime. So x prime could take any value from minus infinity to plus infinity. So this is what I forgot to mention. Okay, so the x coordinate of the particle could take any value from minus infinity to plus infinity. Likewise, y and z component of a position of a particle could also take any value from minus infinity to plus infinity. Okay, so this is where we're integrating over all the possible value. Okay, so this is the identity operator for states of a particle in 3 dimensions. Okay, so this means that if phi is any state of a particle in 3 dimensions, then if you add this thing, then you should get the same state again. Okay. Okay, so this notation is very long. Okay, so it's kind of tedious to write this equation again and again. So instead of this, what we're going to do is that okay, so here, so dx prime, dy prime, dz prime. So I'll just write it in this way. Okay? So I'll just write it as d cube both face x prime. And this one we already use both face x prime. Okay, to denote this, and likewise I'll use this also to. So I'll use both face x prime to also denote this. Okay, so here, so instead of this, we will simply denote this identity operator in this way. Okay, so it is d cube both face x prime, and then we have this ket and bra state. So here it is understood that this is a 3-dimensional integral. Okay, so it's understood that this is actually this 3-dimensional integral, 3-dimensional integral, and the integration is done over the entire space, or you can say the integration is over the entire universe. Okay, so this is the identity operator. So once we have the identity operator, then we should be able to write. So if we have a state psi, we should be able to express. So we should be able to express how the state is given in terms of the position eigenstates. Okay. Or in other words, the expansion of any state in terms of the position eigenstates can be obtained by acting the identity operator on the state psi. Okay, so this is what the same thing as what we have done for 1 dimension. So the state psi is the same as the identity operator acting on the state psi. So here we insert the expression for the identity operator this way, and we can take this state psi inside the integration. Okay, so if we take it inside the integration, then it will be so this means that we have an inner product between this one and this one. Okay, so this is what we have. So inner between both face x prime and psi. So you can take this to the left hand side. So this is what we have. So here inside the integral, this is a number, all right? So d cube x, both face x and x prime, and this inner product is a number. So we have a number multiplying a state. Okay, so here we're integrating overall. So overall the space, overall the possible value of x prime, all right? So this equation tells us how the state psi is expressed as a linear combinations of the position eigenstates. Okay, it tells us how the state psi is given as a linear sum, or how this state psi is given as a sum of the as a sum of all the position eigenstates. Okay, so now, so what I have to say now is that so this thing here, so this thing, so this quantity is something which you're already familiar with. Okay, so this is nothing but the wave function, or in other words, this is the wave function, the value of the wave function at x prime. Okay, uh, x prime, y prime, z prime. Okay, so this is it's difficult to denote voltage. Okay, so this is nothing but the value of the wave function at x prime, y prime, z prime. Okay, uh, so this is the position space wave function. Okay, so this is what I've just said. Okay, so this inner product is just the value of the wave function at x prime, y prime, z prime. So the reason that I'm calling this position wave function is that there's another wave function, which is the momentum space wave function. Okay. Anyway, in your BSc, you have used only the position wave function. Okay. Okay. So we may also write. So instead of the inner product, if you just write the wave function, this is how you can express the state psi in terms of the position eigenstates. So we'll talk more about wave function afterwards. Okay, so now let's talk about the inner product, how to express the inner product between, say, this say psi and phi. In terms of the this, how do we express? So how do we express this inner product in terms of this inner product of x prime and phi and inner product of x prime and phi? Okay, so these are just a wave function, right? So how do we express the inner product like this in terms of the wave function of psi and phi? So in order to do this, so what we can do is we can again insert the int operator here. Okay, so we insert it like this, and then we just substitute the expression for the int operator, which is given here. Okay, so we have this state psi identity operator and the phi, and we can take this state psi and phi inside the integral. Uh, so so if we do this, then so we have to take the inner product between x prime and phi. So this is what we have. Likewise, the inner product between this and this one we'll also get. So this gives us this thing. So here, so what we can do again is instead of this, okay, we can flip this. So we can flip the order x prime and phi, but I also have to put a star here. Okay, so this is what I have done. Okay, so this is the inner product between psi and phi. So what about the inner product between the same state? What about psi and psi? So for that, we just have to replace this by phi. Okay, so if I replace this by phi, then I just have to replace this by. So I have to, yeah. Okay, so this is what I have. So okay, so this is what we have. So again, this is just the mod square. So we have some quantity size, some quantity star, and this is the same quantity. So this is nothing but the mod square of inner product between x prime and psi. Okay, so in terms of this, so we have this thing is equal to this. Okay, so this means that the normalization condition that psi is equal to 1 is given by this, right? Or this one. So this is the normalization condition. So this normalization condition is same as the thing here. Okay, I think I think I can still talk about measurement. Okay, so lastly, let's talk about measurement. Uh, so if a particle is in state psi, so for one dimension we have already said that we cannot interpret this as the probability of finding the. Uh, so here, if x prime is both phase x prime is x prime, y prime, and z prime. Okay, so we cannot interpret this as the probability of finding the particle at this particular point when we measure its position. Okay, so instead we have to interpret this quantity as the probability density. Okay, so probability density in the sense that it is the probability per unit volume. Okay, so it is probability per unit volume. So in order to find the probability, you have to multiply a volume. Okay, so more precisely, if we have a small volume dV. Okay, so let's consider this small region. So the volume of this small region is dV. Okay, so the point. Uh, so this region encloses this point x prime, y prime, z prime. Okay. So the probability of finding the particle within this. So if the particle is in the state psi, so the probability of finding the particle within this small region is given by this. Okay. So in that product between the position eigenstates x prime, y prime, z prime, and then the state psi, and then we have to multiply this by the volume. Okay. Since we are working in Cartesian coordinate, it is useful. Okay, so instead of this region, we can just take a cuboid, uh, something like this. Okay, so we have a cuboid. So the point, so x prime is this the point which is you can think of this x prime as at the center of this cuboid. Uh, so the length of the sides of this cuboid. Okay, so this is the x prime. So the height is dz prime, and the length is dy prime. Okay, so this means that the volume of this cuboid is dx prime, dy prime, dz prime. Okay, so the probability of so if the particle is in the state psi, okay, so the probability of finding the particle within this cuboid when we measure the position of the particle is given by this formula. Okay, so it's just given by this formula where we have to multiply this thing by the volume. Okay, or I can just write this as a. So if you write this as a bold face, yeah, since I've already written here. Okay, so this is the probability of finding the particle within this cuboid. Okay, so here we have assumed that this cuboid will be very small, such that this the state psi does not change much within this cuboid. So instead, if you want to find the probability within a finite volume, okay, so for example, if you want to say within a larger volume, so what you can do is that you can divide this region into small okay, cuboid like this, and then you can use the form. So you can use this formula to find the probability for each of these small volume. Okay, so you use this formula to find the probability for each of these small volume, and then the total probability, you add up all this probability for each of these region. Okay, so in other words, uh, okay, so in other words, if you have a particle in state psi, the probability of finding the particle within a region V is given by this. Okay, so this is a spatial. So V is a spatial region. V is a spatial region. So if you want to find the probability of finding the particle within this spatial region, so you just have to integrate this over the spatial region. So you can also take this. So if you take this V to be all of space, okay. So if you take this to be the entire space of our universe, then the probability has to be one because the particle has to be somewhere. Okay? So whenever you measure the particle, it has to be somewhere inside the universe. So in other words, the probability has to be one. Okay, so this means that so if we so if we integrate this over the entire space, so this has to be one. Okay, so if you look at this, this is same as this one. Okay, so this equal to one is the same as the thing which I've just shown you. Okay, so this means that if we want to interpret this as the probability density, then we have to properly normalize our state such that this is satisfied. Okay. All right. So are there any question? Okay. So tomorrow we will look at position. So we have already talked about position. So tomorrow we'll look at momentum.
Sir,
Yeah. Yes.
uh, in the beginning, you given that example x is equal to if the x get state is equal to 0.9 centimeter, and that means the particle is at 0.9 centimeter. That, I thought that information was given only by eigenvalues. Can you please explain that part?
Oh. Okay. Yeah. I mean, if it is in this x, okay. Uh, so so this means that this is an eigenstate of x hat. Okay. Uh, so this means that this is an eigenstate of oh. Uh, so what I have to say is that the so x prime. So the eigenvalue of x prime could be any number. So it could be any number between minus infinity to plus infinity. Okay.
Yes, sir. Yes, sir.
So so if you could so if you try to find the location of a particle, so it could be anywhere. So you could get any number. So I think I was saying 0.65, right? Centimeter. So here, so any number is possible here. Okay. So here x prime could be any number. So this is what we mean by continuous eigenvalue, because so x prime does not take a discrete value; it could take any number.
Thank you, sir.
Okay, so yeah, so the other thing is that we have said that the possible result of a measurement are only the eigenvalue of the operator. So here, since the eigenvalue of the of x prime, so since the eigenvalue of x prime is minus infinity to plus infinity. So if a particle is in any state psi, so when we measure its position, then we could get any number between minus infinity and plus infinity. So this would be different from trying to measure its energy, okay? Because energy will be usually discrete, so it will not take any continuous value. So So if position could be anywhere between this, but energy will be discrete. Okay, thing like this. Okay, so one last comment which I have to say is that position eigenstates are not very good states. Okay, so in nature there is it's not possible to have a states in position eigenstates. So this is not a good state. Uh, this is not a good state because this is not, you cannot normalize this, as we have seen. So for example, if you take this, this is infinity. Okay, if you so we want psi to be one, but if we have but if you take the inner product of position eigenstate with itself, so it is infinity. So this means that this is not a good state, right? But even though it is not a good state, we can use this state to construct a good state. Okay? So we can construct a state which can so we can use this state to construct other state which can be normalized. Yeah. So you have to remember that in nature we can never have a state like this. Okay. So are there any other questions?
Sir,
Yeah. Yes.
yes, sir. Sir, I want to ask that what books we can follow for
Oh.
this. So,
Uh, so you can look at uh, modern quantum mechanics by J.J. Sakurai. But his notation is different from my notation, a bit different from my notation. Okay, so yeah, so it is different from my notation because for operator I use, for example, I use head to differentiate an operator from the ordinary number. Okay, so he does not use this convention, but anyway, you will still be able to understand it.
thank you, sir.
So you can look at chapter 1, I think. So far what we have done is you can find in chapter 1 of Sakurai. Okay, so are there any other questions? All right, so if there are no other questions, then we can end the class for today.